Image classification using Keras. My name is Richard Kirshner with the Simplilearn team. That's www.simplilearn.com. Get certified, get ahead. And we're going to take a look at image classification using Keras and the basic setup. And we'll actually look at two different demos on here. What's in it for you today? What is image classification? Intel image classification data, creating neural networks with Keras, and the VGG16 model. What is image classification? The process of image classification refers to assigning classes to an entire image. Images can be classified based on different categories like whether it is a nighttime or daytime shot, what the image represents, etc. And you can see here we have mountains looking for mountains. We'll actually be doing some pictures of scenery and stuff like that. In deep learning, we perform image classification by using neural networks to extract features from images and classifies them based on these features. And you can see here where it says like what computer sees, and it says, oh yeah, we see mostly forest, maybe a little bit of mountains because of the way the image is. And this is really where one of the areas that neural networks really shines. If you try to run this stuff through more like a linear regression model, you'll still get results, but the results kind of miss a lot of things as the neural networks get better and better at what they do with different tools we have out there. So Intel image classification data. The data being used is the Intel image classification data set, which consists of images of 6 types of land areas. And so we have forest, building, glaciers, and mountains, sea, and street. And you can see here is a couple of the images out of there as a setup in the Intel image classification data that they use. And then we're going to go into creating a neural networks with Keras. The convolutional neural network that we are creating from scratch looks as shown below. You'll see here we have our input layer. They haven't listed max pooling. So you have, as you're coming in with the input layer, and the input layer is actually before this, but the first layer that it's going to go into is going to be a convolutional neural network. Then you have a max pooling that pulls the convolutional neural network's returns. In this case, they have 2 of those. That is very standard with convolutional neural networks. One of the ones that I was looking at earlier that was standard being used by one of the larger companies, I can't remember which one, for doing a large amount of identification, had 2 convolutional neural networks, each with their max pooling, and then about 17 dense layers after it. We're not going to do that heavy duty of a code, but we'll get you headed in the right direction, and that gives you an idea of what you're actually going to be looking at when you look at the flattened part and then the dense. We're talking like 17 dense layers afterwards. I find that a lot of the stuff I've been working on, I end up maxing it out right around 9 dense layers. It really depends on what you have going in and what you're working with. And the VGG16 model. VGG16 is a pre-trained CNN model which is used for image classification. It is trained on a large, varied data set and fine-tuned to fit image classification data sets with ease. And you can see down here we have the input coming in, the convolutional neural network 1-to-1, 1-to-2, and then pooling. And then we do 2-to-1, 2-to-2 convolutional neural network, then pooling, 3-to-2, and you can see there's just this huge layering of convolutional neural networks. And in this case, they have 5 such layers going in, and then you have 3 dense going out, or more. Now, when they took this setup, this actually won an award back in 2019 for this particular setup. And it does really good, except that, again, we only show the 3 dense layers here. And as you find out, depending on your data going in and what you have set up, that really isn't enough on one of these setups. And I'm going to show you why we restricted it, because it does take up a lot of processing power in some of these things. So let's go ahead and roll up our sleeves, and we're going to look at both the setups. We're going to start with the first classification and then we'll go into the VGG16 and show you how that's set up. Now I'm going to be using Anaconda, and let me flip over to my Anaconda so you can see what that looks like. Now I'm running in the Anaconda here. You'll see that I've set up a main Python 3.8. I always put that in there because this is where I'm doing like most of my kind of playing around. This is done in Python version 3.8. We're not going to dig too much into versions. At this point you should already have Keras installed on there. Usually Keras takes a number of extra steps. And then our usual setup is the NumPy, the pandas, your scikit, which is going to be the sklearn, your Seaborn, and I'll show you those in just a minute. And then I'm just going to be in the Jupyter lab where I've created a new notebook in here. And let's flip on over there to my blank notebook. Now, there's a couple cool things to note in here is that, one, I use the Anaconda Jupyter Notebook setup because it keeps everything separate, except for Keras. Keras is actually running separately in the back. I believe it's a C program. What's nice about that is that it utilizes the multiprocessors on the computer, and I'll mention that just in a little bit when we actually get down to running the code. And when we look in here, the couple things to note is here's our, oops, I thought I grabbed the other drawing thing. But here's our NumPy and our pandas right here and our operating system. This is our scikit. You always import it as sklearn for the classification report. We're going to be using, well, usually import like Seaborn brings in all of your PyPlot library also. Kind of nice to throw that in there. I can't remember if we're actually using Seaborn, if they just, the people in the back just threw that together. And then we have the sklearn shuffle for shuffling data. Here's our matplotlib library that the Seaborn is pretty much built on. CV2, if you're not familiar with that, that is our image module for importing the image. And then of course we have our TensorFlow down here, which is what we're really working with. And then the last thing is just for visual effect while we're running this. If you're doing a demo and you're working with the partners or the shareholders, this TQDM is really kind of cool. It's an extensible progress bar for Python. And I'll show you that too. Remember, data science is not, I mean, you know, most of this code, when I'm looking through this code, I'm not going to show half of this stuff to the shareholders or anybody I'm working with. They don't really care about pandas and all that. We do, because we want to understand how it works. So we need to go ahead and import those different setup on there. And then the next thing is we're going to go ahead and set up our classes. Now we remember if we had mountain, street, glacier, building, sea, and forest, those were the different images that we have coming in. And we're going to go ahead and just do class name labels, and we're going to kind of match that class name of I for I, class name equals the class names. So our labels are going to match the names up here. And then we have the number of classes, and print the class names and the labels. And we'll go ahead and set the image size. This is important that we resize everything, because if you remember with neural networks, they take one size data coming in. And so when you're working with images, you really want to make sure they're all resized to the same setup. It might squish them, it might stretch them. That generally does not cause a problem in these. And some of the other tricks you can do with, if you need more data, and this is one that's used regularly, we're not going to do it in here, is you can also take these images and not only resize them, but you can tilt them one way or the other, crop parts of them, so that they process slightly differently. And it'll actually increase your accuracy of some of these predictions. And so you can see here we have mountain equals 0, that's what this class name label is. Street equals 1, glacier equals 2, buildings equals 3, C4, forest equals 5. Now, we did this as an enumerator, so each one is 0 through 5. A lot of times we do this instead as 0, 1, 0, 1, 0, 1, so you have 5 outputs and each one's a 0 or a 1 coming out. So the next thing we really want to do is we want to go ahead and load the data up, and just put a label in there, loading data. Just so you know what we're doing, I'm going to put in the loading data down here. Make sure it's well labeled. And we'll create a definition for this. And this is all part of your pre-processing. At this point, you could replace this with all kinds of different things depending on what you're working on. And once you download, you can go download this data set, send a note to the Simplilearn team here in YouTube, and they'll be happy to direct you in the right direction. And make sure you get this path here, so you have the right, wherever you saved it. A lot of times I'll just abbreviate the path or put it as a sub thing and just get rid of the directory. But again, double check your paths. We're going to separate this into a segment for training and a segment for testing. And that's actually how it is in the folder. And let me just show you what that looks like. So when I have my lengthy path here where I keep all my programming Simplilearn, this particular setup we're working on, image classification and image classification. Clearly you probably wouldn't have that lengthy of a list. And when we go in here, you'll see sequence train, sequence test. They've already split this up. This is what we're going to train the data in. And again, you can see buildings, forest, glacier, mountain, sea, street. And if we double click, let's go under forest. You can see all these different forest images. And there's a lot of variety here. I mean, we have wintertime, we have summertime. So it's kind of interesting. You know, here's like a fallen tree versus a road going down the middle. That's really hard to train. And if you look at the buildings, a lot of these buildings, you're looking up a skyscraper, we're looking down the setup. Here's some trees with one. I want to highlight this one. It has trees in it. Let me just open that up so you can see it a little closer. The reason I want to highlight this is I want you to think about this. We have trees growing. Is this the city or a forest? So this kind of imagery makes it really hard for a classifier. And if you start looking at these, you'll see a lot of these images do have trees and other things in the foreground, weird angles. Really a hard thing for a computer to sort out and figure out whether it's going to be a forest or a city. And so in our loading of data, one, we have to have the path, the directory. We're going to come in here, we have our images and our labels. So we're going to load the images in one section, the labels in another. And if you look through here, it just goes through the different folders. In fact, let me do this. There we go. As we look at this, we're just going to loop through the 6 different folders that have the different landscapes. And then we're going to go through and pull each file out and each label. So we set the label, we set the folder for file and list. Here's our image path, join the paths. This is all kind of general stuff, so I'm kind of skipping through it really quick. And here's our image setup. If you remember, we're talking about the images. We have our CV2 reader, so it reads the image in. It's going to go ahead and take the image and convert it to from blue, green, red to red, green, blue. This is a CV2 thing. Almost all the time it imports it, and instead of importing it as a standard that's used just about everywhere, it imports it with the BGR versus RGB. RGB is pretty much a standard in here. You have to remember that was CV2. And then we're going to go ahead and resize it. This is the important part right here. We've decided what the size is, and we want to make sure all the images have the same size on them. And then we just take our images and we're just going to append the image, append the label, and then the images is going to turn into a numpy array. This just makes it easier to process and manipulate. And then the labels is also a numpy array. And then we just return the output, append images and labels, and we return the output down here. So we've loaded these all into memory. We haven't talked much. There'd be a different setup in there because there is ways to feed the files directly into your Keras model. But we want to go ahead and just load them all because it's really, for today's processing and what our computers can handle, that's not a big deal. And then we go ahead and set the train images, train labels, test images, test labels, and that's going to be returned in our output append. And you can see here we did images and labels set up in there, and it just loads them in there. So we'll have these 4 different categories. Let me just go ahead and run that. So now we've gone ahead and loaded everything on there. And then if you remember from before, we imported, let me just go back up there, Shuffle. Here we go. Here's our sklearn utilities import shuffle. And so we want to take these labels and shuffle them around a little bit, just mix them up so it's not having the same, if you run the same process over and over, then you might run into some problems on there. And just real quick, let's go ahead and do a plot so we can just, we've looked at them as far as from outside of our code. We pulled up the files and I showed you what that was going on. We can go ahead and just display them here too. And I tell you, when you're working with different people, this should be highlighted right here. This thing is like when I'm working on code and I'm looking at this data and I'm trying to figure out what I'm doing, I skip this process. The second I get into a meeting and I'm showing what's going on to other people, I skip everything we just did. So, and go right to here where we want to go ahead and display some images and take a look at it. And in this display, I've taken them and I've resized the images to 20 by 20. That's pretty small. So we're going to lose just a massive amount of detail. And you can see here these nice pixelated images. I might even just stick with the folder showing them what images we're processing. Again, this is, you gotta be a little careful of this. Maybe resizing it was a bad idea. In fact, let me try it without resizing it and see what happens. Oops. So I took out the image size and then we put this straight in here. One of the things, again, this is, put the D, there we go. One of the things, again, that we want to note whenever we're working on these things is the CV2, there are so many different image classification setups. It's really a powerful package when you're doing images. But you do need to switch it around so that it works with the PyPlot. And so make sure you take your NumPy array and change it to a uinteger8 format because it comes in as a float. Otherwise you'll get some weird images down there. And so this is just basically we've split up, or we've created a plot. We went ahead and did the plot 20 by 20, or the plot figure size is 20 by 20. And then we're doing 25, so a 5 by 5 subplot. Nothing really going on here too exciting, but you can see here where we get the images. And really when you're showing people what's going on, this is what they want to see. So you skip over all the code and you have your meeting, you say, okay, here's our images of the building. Don't get caught up in how much work you do, get caught up in what they want to see. So if you want to work in data science, that's really important to know. And this is where we're going to start having fun. Here's our model. This is where it gets exciting when you're digging into these models. And you have here, let me get, there we go. When you have here, if you look here, here's our convolutional neural network 2D. And 2D is an image. You have 2 different dimensions, X, Y, and even though there's 3 colors, it's still considered 2D. If you're running a video, you'd be convolutional neural network 3D. If you're doing a series going across, a time series, it might be 1D. And on these, you need to go ahead and have your convolutional neural network. If you look here, there's a lot of really cool settings going on to dig into. We have our input shape, so everything's been set to 150 by 150. And it has, of course, 3 different color schemes in it. That's important to notice. Activation default is ReLU. This is small amounts of data being processed on a bunch of little neural networks. And right here is the 32. That's how many of these convolutional neural networks are being strung up on here. And then the 3 by 3, when it's doing its steps, it's actually looking at a little 3 by 3 square on each image. And so that's what's going on here. And with convolutional neural networks, the window floats across and adds up all these numbers going across on this data. And then eventually it comes up with 30, in this case, 32 different feature options that it's looking for. And of course, you can change that 32. You can change the 3 by 3, so you might have a larger setup. You know, if you're going across 150 by 150, that's a lot of steps. So we might run this as 15 by 15. There's all kinds of different things you can do here. We're just putting this together. Again, that would be something you would play with to find out which ones are going to work better on this setup. And there's a lot of play involved. That's really where it becomes an art form, is guessing at what that's going to be. The second part I mentioned earlier, and I can only begin to highlight this. When you get to these dense layers, one is the activation is a ReLU. They use a ReLU and a softmax here. It's a whole setup just explaining why these are different and how they're different, because there's also an exponential, there's a tangent. In fact, there's just a ton of these, and you can build your own custom activations depending on what you're doing. A lot of different things go into these activations. There are 2 or 3 major thoughts on these activations, and ReLU and softmax are, well, ReLU, you're really looking at just the number, you're adding all the numbers together, and you're looking at Euclidean geometry, ax plus bx2 plus cx3 plus bias. With softmax, this belongs to the party of it's activated or it's not, except they call it softmax because when you get to 0, instead of it just being 0, it's actually a little bit less than 0, so that when it trains, it doesn't get lost. There's a whole series of these activations. Another activation is the tangent, where it just drops off and you have like a very narrow area where you have from -1 to 1, or exponential, which is 0 to 1. So there's a lot of different ways to do the activation. Again, we can do, that'd be a whole separate lesson on here. We're looking at the convolutional neural network, and we're doing the 2 pools. This is so common. You'll see two convolutional neural networks stacked on top of each other, each with its own max pool underneath. And let's go ahead and run that. So we built our model there, and then we need to go ahead and compile the model. So let's go ahead and do that. We are going to use the Atom optimizer. The bigger the data, the Atom fits better on there. There's some other optimizer, but I think Atom's a default. I don't really play with the optimizer too much. That's like once you get a model that works really good, you might try some different optimizers, but Atom's usually the most. And then we're looking at loss. Pretty standard. We want to minimize our loss. We want to maximize the loss of error. And then we're going to look at accuracy. Everybody likes the accuracy. I'm going to tell you right now, I start talking to people and I'm like, okay, what's the loss on this and that? And as a data science, yeah, I want to know how what's going on with that, and we'll show you why in a minute. But everybody wants to see accuracy. They want to know how accurate this is. And then we're going to run the fit. And I wanted to do this just so I can show you, even though we're in Python setup in here where Jupyter Notebook is using only a single processor, I'm going to bring over my little CPU tool. This is 8 cores on 16 dedicated threads, so it shows up as 16 processors. And actually, I got to run this and then move it over. So we're going to run this, and hopefully it doesn't destroy my mic. And as it comes in, you can see it's starting to go through the epochs. And I set it for 5 epochs. And then this is really nice because Keras uses all the different threads available. So it does a really good job of doing that. This is going to take a while. If you look at here, it's ETA 2 minutes and 25 seconds, 24 seconds. So this is roughly 2.5 minutes per epoch. And we're doing 5 epochs. So this is going to be done in roughly 15 minutes. I don't know about you, but I don't think you want to sit here for 15 minutes watching the green bars go across. So we'll go ahead and let that run. And there we go. There was our 15 minutes. It's actually less than that. because I did, when I went in here, realize that, where was it? Here we go. Here's our model compile. Here's our model fit. And here's our epochs. So I did 4 epochs. So a little bit better, a little more like 10 to 11 minutes instead of doing the full 15. And when we look at this, here's our model. We talked about the compiler. Here's our history. We're going to history equals the model fit. We'll go into that in just a minute. And what we're looking at is we have our epochs. Here's our validation split. So as we train it, we're weighing the accuracy versus, you kind of pull some data off to the side while you're training it. And the reason we do that is that you don't want to overfit. And we'll look at that chart in just a minute. Here's batch size. This is just how many images you're sending through at a time. The larger the batch, it actually increases the processing speed. And there's reasons to go up or down on the batch size because of the smaller the batch. There's a certain point where you get too large of a batch and it's trying to fit everything at once. So 128 is kind of big. Depends on the computer you're on and what it can handle. And then of course we have our train images and our train labels going in telling it what we're going to train on. And then we look at our 4 epochs here. Here's our accuracy. We want the accuracy to go up, and we get all the way up to 0.83 or 83%. This is actual percentage based pretty much. And we can see over here our loss. We want our loss to go down. Really fluctuates. 55, 1.2, 0.77, 0.48. So we have a lot of things going on there. Let's go ahead and graph those. Turn that off. And our team in the back did a wonderful job of putting together this basic plot setup. Here's our subplot coming in. We're going to be looking at, from the history, we're going to send it the accuracy and the value accuracy labels and set up on there. And we're going to also look at loss and value loss. So you can see what this looks like. What's really interesting about this setup, and let me just go ahead and show you, because without actually seeing the plots, it doesn't make a whole lot of sense. It's just basic plotting of the data using the PyPlot library. And I want you to look at this. This is really interesting. When I ran this the first time, I had very different results, and they vary greatly. And you can see here our accuracy continues to climb. And there's a crossover here. Put it in here. Right here's our crossover. And I point that out because as we get to the right of that crossover where our accuracy, and we're like, oh yeah, I got 0.8%, we're starting to get an overfit here. That's what this switchover means. As our value, as a training set versus the value accuracy stays the same. And so that this is the one we actually really want to be aware of, and where it crosses is kind of where you want to stop at. And we can see that also with the train loss versus the value loss right here. We did 1 epoch, and look how it just flatlines right there with our loss. So really 1 epoch is probably enough, and you're going to say, wow, okay, 0.8%. Certainly if I was working with the shareholders, telling them that it has an 80% accuracy isn't quite true. And we'll look at that a little deeper. It really comes out here that the accuracy of our actual values is closer to 0.41% right here, even after running it this number of times. And so you really want to stop right here at that crossover. 1 epoch would have been enough. So the data is a little overfitted on this when we do 4 epochs. And, oops, there we are. Okay. My drawing won't go away. Let me see if I can get, there we go. For some reason, I've killed my drawing ability and my recorder. All right, took a couple extra clicks. So let's go ahead and take a look at our actual test loss. So you see where it crosses over. That's where I'm looking at. That's where we start overfitting the model. And this is where if we were going to go back and continually upgrade the model, we would start taking a look at the images and start rotating them. We might start playing with the convolutional neural network instead of doing the 3x3 window. We might expand that, or find different things that might make a big difference as far as the way it processes these things. So let's go ahead and take a look at our test loss. Now remember, we had our training data. Now we're going to look at our test images and our test labels for our test loss here. And this is just model evaluate, just like we did fit up here. Where was it? One more. Model fit with our training data going in. Now we're going to evaluate it on the, and this data has not been touched yet. So this model's never seen this data. This is on completely new information as far as the model is concerned. Of course, we already know what it is from the labels we have. And this is what I was talking about. Here's the actual accuracy right here, 0.48 or 4847. So this 49% of the time guesses what the image is. And I mean, really, that's the bottom dollar. Does this work for what you're needing? Does 49% work? Do we need to upgrade the model more? In some cases, this might be, what was I doing? I was working on stock evaluations, and we were looking at what stocks were the top performers. Well, if I get that 50% correct on top performers, I'm good with that. That's actually pretty good for stock evaluation. In fact, the number I had for stock was more like 30-something% as far as being a top performer stock. Much harder to predict. But at that point, you're like, well, you'll make money off of that. So again, this number right here depends a lot on the domain you're working on. And then we want to go ahead and bring this home a little bit more as far as looking at the different setup in here. And one of the, from Sklearn, if you remember, actually let's go back to the top, we had the classification report. And this came in from our Sklearn or scikit setup. And that's right here. You can see it right here on the, there we go, classification report right here. Sklearn metrics, import classification report. That's what we're going to look at next. A lot of this stuff depends on who you're working with. So when we start looking at precision, this is like for each value, I can't remember what one was probably mountains. So if 44% is not good enough, if you're doing like, you're in the medical department and you're doing cancer, is this cancerous or not? And I'm only 44% accurate. Not a good deal. I would not go with that. So it depends on what you're working with on the different labels and what they're used for. Facebook, 44%, I'm guessing the right person. I would hope it does a little bit better than that. But here's our main accuracy. This is what almost everybody looks at. They say, oh, 48%, that's what's important. Again, it depends on what domain you're in and what you're working with. And now we're going to do the same model. Oops, somehow I got there it goes. I thought I was going to get stuck on there again. This time we're going to be using the VGG16. And remember, this one has all those layers going into it. So it's basically a bunch of convolutional neural networks getting smaller and smaller on here. And so we need to go ahead and import all our different stuff from Keras. We're importing the main one is the VGG16 setup on there. Just aim that, there we go. There's kind of a pre-processing images, applications, pre-process input. This is all part of the VGG16 setup on there. And once we have all of those, we need to go ahead and create our model. And we're just going to create a VGG16 model in here, inputs, model inputs, outputs, model inputs. I'm not going to spend as much time as I did on the other one. We're going to go through it really quickly. one of the first things I would do is, if you remember in Keras, you can treat a model like you would a layer. And so at this point, I would probably add a lot of dense layers on after the VGG16 model and create a new model with all of those things in there. And we'll go ahead and run this because here's our model coming in and our setup. And it'll take it just a moment to compile that. Hey, what's funny about this is I'm waiting for it to download the package. Since I pre-ran this, it takes it about a couple minutes to download the VGG16 model into here. And so we want to go ahead and train features for the model. We're going to predict the train images, and we're going to test features on the predict test images on here. And then I told you I was going to create another model 2, and the people in the back did not disappoint me. They went ahead and did just that. And this is really an important part. This is worth stopping for. I told you I was going to go through this really quick. So here's our, we have our model 2 coming in. And we've created a model up here with the VGG16 model equals model inputs. And so we have our VGG16. This has already been pre-programmed. And then we come down here, and I want you to notice on this right here, model 2 layers -4 to 1, x layer x. We're basically taking this model and we're adding stuff onto it. And so we've just basically duplicated this model. We could have done the same thing by using model up here as a layer. We could have had the input go to this model and then have that go down here. So we've added on this whole setup, this whole block of code from 13 to 17 has been added on to our VGG16 model. And we have a new model with the layer, input, and X down here. Let's go ahead and run that and compile it. And that was a lot to go through right there. When you're building these models, this is the part that gets so complicated that you get stuck playing in, and yet it's so fun. It's like a puzzle. How can I loop these models together? And in this case, you can see right here that the layers, we're just copying layers over and adding each layer in. This is one way to build a new model. And we'll go ahead and run that. Like I said, the other way is you can actually use the model as a layer. I had a little trouble playing with it. Sometimes when you're using the straight model over, you run into issues. And it seems like it's going to work, and then you mess up on the input and the output layers. There's all kinds of things that come up. Let's go ahead and do the new model. We're going to compile it. Again, here's our metrics: accuracy, sparse categorical loss. Pretty straightforward, just like we did before. You got to compile the model. And just like before, we're going to create a history. The history is going to be new model fit train 128. And just like before, if you remember when we started running this stuff, we're going to have to go ahead and it's going to light up our setup on here. And this is going to take a little bit to get us all set up. It's not going to just happen in a couple minutes. So let me go ahead and pause the video and run it, and then we'll talk about what happened. Okay, now when I ran that, these actually took about 6 minutes each. So it's a good thing I put it on hold. We did 4 epochs. Actually, I had to stop it because it was at 10 and switch it to 4 because I didn't want to wait an hour. And you can see here our accuracy and our loss numbers going down. And just at a glance, it actually performed, if you look at the accuracy, 0.2658. So our accuracy is going down, or 26%, 34%, 35%. And you can see here at some point it just kind of kicks the bucket. Again, this is overfitting. That's always an issue when you're running on programming these different neural networks. And then we're going to go ahead and plot the accuracy history. We built that nice little subroutine up above, so we might as well use it. And you can see it right here. There's that crossover again. And if you look at this, look how the red shifts up, how our loss functions and everything crosses over. we're overfitting. After one epoch, we're clearly not helping the problem or doing better. It's just gonna baseline. This one actually shows with the training versus the loss, value loss, maybe second epoch. So on here, we're now talking more between the first and the second epoch, and that also shows kind of here. So somewhere in here, it starts overfitting. And right about now, you should be saying, uh-oh, something went wrong there. I thought that when we went up here and ran this, look at this. We have the accuracy up here is hitting that 48%, and we're down here. You look at the score down here, that looks closer to 20%, not nearly anywhere in the ballpark of what we're looking for. And we'll go ahead and run it through the actual test features here. And there it is. We actually run this on the unseen data and everything, 0.18 or 18%. I don't know about you, but I wouldn't want, at 18%, this did a lot worse than the other one. I thought this was supposed to be the super model, the model that beats all models, VGG16 that won the awards and everything. Well, the reason is that one, we're not pre-processing the data, so it needs to be more. There needs to be more as far as like rotating the data at 45-degree angle, taking partials of it, so you can create a lot more data to go through here. And that would actually greatly change the outcome on here. And then we went up here, we only added a couple dense layers. We added a couple convolutional neural networks. This huge pre-trained setup is looking for a lot more information coming in as far as how it's going to train. And so this is one of those things where I thought it would have done better. And I had to go back and research it and look at it and say, well, why didn't this work? Why am I getting only 18% here instead of 44% or better? And that would be why, is it doesn't have enough training data coming in. And again, you can make your own training data. So it's not that we have a shortage of data, it's that some of that has to be switched around and moved around a little bit. And this is interesting right here too. If you look at the precision, we're getting it on number 2, and yet we had 0 on everything else. So for some reason, it's not seeing the different variables in here. So it'd be something else to look in and try to track down. And that probably has to do with the input. But you can see right here, we have a really good solid 0.48 up here. And that's where I'd really go with, is starting with this model. And then we look at this model and find out, why are these numbers not coming up better? Is it the data coming in? Where's the setup on there? And that is the art of data science right there, is finding out which models work better and why. And we went through the very basics of convolutional neural networks along with the VGG16 import and how you can get started with that. And again, the art is the data going in and learning to play with it, find out what works. Thank you for joining us today with Simplilearn. Again, my name is Richard Kirshner with the Simplilearn team. For more information, please visit www.simplilearn.com. Get certified, get ahead.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.